This video is on titration curves, or pH curves. So our aims for this video are to be able to draw titration curves through reactions of strong and weak acids with strong and weak bases. That'll be 4 different curves. One for a strong acid with a strong base, one for a strong acid with a weak base, one for a weak acid with a strong base, and one for a weak acid with a weak base. You can then use those titration curves to choose an appropriate indicator for your titration. So in year 12 you may have noticed we use different indicators depending on which acid and base we were using. You'll understand why after this video. And lastly, explain why there might be more than one equivalence point. We'll discuss what that means in a second in a titration curve. So titration curves are basically a graph to show the change in pH as you add acid to an alkali or vice versa. For each of the titration curves I'm going to show you, I'm going to be adding the acid to the alkali. And titration curves are important because they help us choose an appropriate indicator when we're trying to work out how much acid or how much alkali is needed to neutralise the other solution. So I'm going to start off by showing the titration curve that happens when, or the change in pH that happens when we add a strong acid to a strong base. So that one's going to be in red. So this one's going to be a strong acid added to a strong base. And what happens is basically if we start off with a strong base, the pH of it is going to be around 14. And if we finish with a strong acid, as we add more acid, it's going to get closer and closer to 1. The pH, that is. But the pH doesn't drop in a proportional manner, if you like. What happens is it stays at around 14 for a while, and then it suddenly drops, and then comes back round to 1. And this area where it suddenly drops is known as the equivalence point. Now, as you can see, the equivalent point, or where it drops, goes through pH 7, which I'll just put in black for you. So there's pH 7. So our indicator that we choose doesn't need to change at pH 7. Some of them change at pH 10. Phenolphthalein is an example. Some of them change below 7. Methyl orange is an example. But because both of those pHs are still on this straight line, even if they change at pH 10 or pH 3 or 4, then it'll still be the same volume that we've added for pH 7. So it doesn't matter if our indicator changes at a different pH as long as it's still on this straight line, this equivalence point. Now, when we add different strength acids to different strength bases, this curve is different, and so that will allow us to judge which indicator we will use. So this green one, I'm going to show you a strong acid with a weak base instead. So this one's going to look like this. So weak base is going to start at a pH of around 10, and for a strong acid it's going to finish at a pH of around 1, so it's going to go across. Our equivalence points is going to be around here, and it's going to level off for 1. So we can't use this time an indicator that changes at 10 because that won't be on our straight line. So this time we've got to use an indicator which changes at around 3 or 4 instead. If we now change to different ones, this one's now going to be a weak acid with a strong base. And so this time the strong base is going to start at 14 and a weak acid is going to finish at around 4. So it's going to again drop suddenly, but it's not going to get anywhere near down to 1 this time, and so we can't really use an indicator that changes at around 3 or 4 because that wouldn't be on the straight line, but we could use an indicator that changes at around 10 instead. The purple one I'm going to show you is a weak acid with a weak base. And you'll see this time, so it's going to start at 10 and finish at around 4. This time, the equivalence point isn't as pronounced, and so there's no straight line, which means that the indicator has to change at 7, really, for this titration to be at all accurate. So how do you put this knowledge into practice? Well, firstly, here's an example question of what you may get asked. So it says a student carried out a titration by adding aqueous solution of sodium hydroxide from burette to an aqueous solution of ethanoic acid. The end point was reached when 22.6 cm³ of the sodium hydroxide solution had been added 25 cm³ of ethanoic acid in a list of indicators shown below. And it says, select from the list the most suitable indicator for the end point of this reaction. So the reason I'm showing you this slide, I'm going to go on to a new slide with just this table on, but you've got to pick out what the acid and alkali are. So the alkali is sodium hydroxide, and the acid was ethanoic acid. So that's going to be sodium hydroxide, which is a strong base, and ethanoic acid, which is a weak acid. So you've got to think, what does the curve look like for those two things added together? If we look at the curve, we'll see, so it was a weak acid with a strong base. We'll start with a strong base, that's around 14 it starts at. Weak acid ends at around 4, so the curve's going to look like that. And 7 is around here. So we've got to look at each indicator in turn and think about which one's going to be most appropriate. So first, thymol blue changes at around 1.2 to 2.8. So thymol blue changes around here. So that one is not going to be appropriate. Bromiophenol blue changes between 3 and 4.6. So that one is going to change around here, which again isn't going to be appropriate. Litmus changes between 5 and 8. So that's around here, so that one might be appropriate. And the last one changes between 7.6 and 9.2, and that one is around here. So I would say that the best one is going to be this one, because it's on the straight line quite clearly. It's not even close to a bit of the curvy bit of the line. So our indicator that we would choose would be cresol purple, and that would be our answer. Now you might get a question that presents you with a pH curve that looks a bit like this, and you can see this time there is more than one equivalence point, and this happens when more than one reaction might happen between an acid and a base. So this titration curve is for the reaction between phosphoric acid and sodium hydroxide, and it's phosphoric acid being added to sodium hydroxide because, as you can see, it's starting at a high pH and ending at a low pH. So phosphoric acid has the, sorry, I'm just going to draw that somewhere else. Phosphoric acid has the formula H3PO4, and sodium hydroxide has the formula NaOH. So what can happen is that one hydrogen can be displaced by a sodium at a time. So at the first equivalence point, the following is happening. So at this first drop, we've got H3PO4 plus NaOH going to make just a monosubstituted one, so NaH2PO4 plus H2O, so that's our salt and water, so acid plus base equals salt and water. And then our next equivalence point, we've got the NaH2PO4 reacting with another NaOH. So here we've got NaH2PO4 reacting with another NaOH to give us Na2HPO4 plus water. And then at our final equivalence point, we've got the last reaction happening, which would be Na2HPO4 plus H2O going to make Na3PO4 plus H2O. Sorry, that shouldn't have been H2O, that should have been NaOH, obviously. Okay, so here we've got three reactions happening, each time one hydrogen being displaced by a sodium. So here, the first one, we've got H2PO4 plus NaOH making NaH2PO4 plus H2O, then another sodium displacing another hydrogen to make Na2HPO4 plus water. That's our second equivalence point. And our third equivalence point, we've got the final substitution to give what we would normally give as the final products of this reaction. Now that can happen with any acid that has more than one hydrogen in it. So sulfuric acid will do exactly the same thing, but sulfuric acid only has two hydrogens in it, so it's H2SO4, which means there would be two equivalence points. And in your assessed homework, you've got a question where you've got to write an equation for the equivalence points, and hopefully you'll be able to do that now.